and welcome to Jedi Lesson 9. This is homework from week 6A on Widely Plus, and we're going to be looking at the first problem in our homework, which states, in an ultra-low temperature experiment, a collection of atoms enter a special state called a Bose-Einstein condensate, in which the index of refraction is 1.67 times 10 to the 7th. What is the speed of light in this condensate? Okay, so given this, I know that the formula that we want to use is going to be, let me change my color. The speed equals c over n. And then I want to go ahead and draw an image so that we could visualize this better, as well as define some of the terms that are going to be helpful to us in this video. So the first thing I'm going to do is draw that diagram. So given that c is our constant, that's like 3.00 times 10 to the 8th meters per second. And then we have our index of refraction for the Bose-Einstein condensate, which is 1.67 times 10 to the 7th. It's going to be our n, and then our n1 here could be 1. And then we're going to go ahead and find the v2 here. I guess this could be v1. Okay, so with that said, we can tell that because this has a slightly higher index, that it's going to be a faster wavelength. So then for our image, I was thinking we can draw like a slow wavelength for this, and then this could be like much faster. And that kind of represents where we're going. I guess this is a much faster increase in speed. It's like right when it hits that, it becomes really, really fast. Please excuse my wavelength drawings. They kind of look like spikes instead of wavelengths. But yeah, so that's kind of an image of what's going on in the background, like what's happening to the length and the speed of the wavelengths. So with that said, we can go on to defining some of the terms that might be of use for us. I know in this equation we have v, c, and n, so we can go ahead and define these over here. So c is the speed of light, and it's a constant that represents the maximum speed at which the energy can travel. So the value is usually what we defined earlier, the 3.00 times 10 to the 8th. And then the SI unit for this is going to be meters per second, because again, we're talking about speed here. So that's what we're going to be using. And then n represents the index of refraction, which we've seen in this problem. They give it to us as 1.67 times 10 to the 7th. So the SI unit for this is none. There's no dimension. And then the last one we want to define is v, which is the speed of light. And the SI unit for this is also meters per second, because again, we're talking about speed. So now that we've defined those terms, we can go ahead and solve this problem. So again, we're looking for the speed of light in this condensate. So we can do v equals c over n. Our c is 3.00 times 10 to the 8th meters per second. And our n is 1.67 times 10 to the 7th. Perfect. And we can substitute those in. Great. And then once you plug that into your calculator, that should give us a value of around 17.96 meters per second. And we can check that, and that checks out. And go ahead and move on to question 2 of our homework for week 6A. And this is more of, I guess, well, this is not a calculation-based problem, so we're going to go ahead and just walk through this and kind of piece things together that we've learned from this unit. So problem 2 says, the drawing shows 2 examples in which a ray of light is refracted at the interface between 2 liquids. In each example, the incident ray is in liquid A and strikes the interface at the same angle of incidence. In one case, the ray is refracted into liquid B, and in the other, it is refracted to liquid C. I'm going to go ahead and highlight some. The dashed lines denote the normals to interfaces. Rank the indices of refraction to the 3 liquids in descending order, largest first. All right, so we know that at the end we want to have kind of a ranking going, and we're going to rank these refractions. So one thing I want to go over is Snell's law, and one of the big takeaways that we learned from Snell's law is that when a light ray is hitting a material that has a higher index, the angle will get smaller, and then when it hits a material that has a lower index, we know that the angle is going to get larger. So this is kind of good to know from our image here. And this drawing helps us see the liquids as well. We have A, B, and C. And we have the normal line, which is where, I should go ahead and define it while I talk about it. But the normal line is something that we look at closely in this. And the normal line is that imaginary line, or this dotted line that we see here, dashed line, that is 90 degrees to the boundary of the surface where the light is coming in. So this is the light here, and we know that the light strikes here. And then once it hits this normal line boundary, which is an imaginary one, it's not actually drawn there, then the light bends this way, which I should draw in a different color. Okay, so this is our normal line. We have the incoming light. And then this is going to be after it bends. Okay, and then another thing that I want to define is the angle of incidence, which is usually seen as this. That was total theta. Okay, that's the angle between the incoming light here, that ray, and the normal line. So it's going to be this, okay? And then the SI unit for angle of incidence is degrees. Then we also have the angle of refraction, which is seen as theta. And then that's the angle between the bent ray that's inside the second material and then the normal line. Also, I'm going to go ahead and draw this next diagram. So we have that incoming light, and then we have the bended light. Okay. And so then to kind of give an idea, I'm going to draw it on the second diagram here. But the angle of refraction is, we could do it in red. It's basically the angle that's made with the refracted ray, which in this case would be that orange, and then the normal line. And it's also, I should note that it's the angle that's made like in the second material. And since these two quadrants are one material and this is another material, then the angle of refraction would be like right here. Okay? And the SI unit for this is also degrees. Just gonna write that. Then the last term I want to go ahead and define is the index of refraction, which we heard about in the last problem, and we just want to revisit it one more time. That's shown by n. And then the SI unit for this is none. And the index of refraction is just a number that kind of shows us the density of a certain material. Okay, now that we've defined all of these, I do want to bring up Snell's law, which I brought up earlier, and it is represented by this equation, which is n1, and then the sine of theta 1 equals n2, and then times the sine of theta 2. So now that we have these descriptions written out, it's great because we can go ahead and kind of, dissect Snell's law. So we know that n1 is that first index of refraction, and then we're going to multiply it by the sine of theta 1, which is the angle of incidence. Then we have n2, which is the second index of refraction we're given, times the sine of theta 2, which is the angle of refraction. So that kind of makes it a little easier to follow. And then now that we have this down, let's go ahead and look at our two images that are provided. So we know that from material A and B, so this first diagram here, the light is bending outwards. So it's going away from this normal line, versus here it's like down. So because it's bending out, then we know that B is going to be greater than theta A. Okay? And then also, oh yeah, one more thing about the Snell's law thing that I went over earlier is the fact that the larger angle will mean that there's a smaller index. So then also we have A is going to be greater than B. Okay? And then now for this next diagram, we have the difference between A and C, and we know that the light kind of goes in closer to the normal line. So this is the normal line again, and this is bending relatively close to that normal line that we have there. So then we know that theta C is going to be less than theta A. And then again, looking at Snell's law, that smaller angle means that there's a larger index. So in this case, it's going to be NC is going to be greater than NA. Okay? And then now that we have this, we can kind of go ahead and pair these together, those two conclusions we made, and we know that NC is going to be greater than NA, and here NA is greater than NB. So we can just order that, put that all together. So we have NC is the greatest, and then we have NA, and that's like a 7, and then NB. And perfect. We can go ahead and see if that checks out. Remember, N is the index of refraction. So we ordered them for the 3 liquids, and perfect. That matches